Fraser. Our fourth talk on the geomechanics side is the mathematical modeling. The student that is working on this is Mahdi Fazaeli, and Mahdi is just getting the microphone done up here. Come on over here, Mahdi, right here. And I mentioned earlier that roof stability was an issue, and it is not clear what kind of model will end up being the best kind of model in the future for roof stability in a salt cavern with air being the fluid. Because remember, air has a capillary entry pressure into the porous rock. So this is a great unknown. There is nothing in the literature that really has helped us a great deal in this problem. So Mahdi is here to present some very preliminary approaches based on a method called a Voussoir beam analysis, which is a beam bending analysis for brittle materials. Please, Mahdi.
Thank you. Hello, everybody. My presentation is about the stability assessment of a roof layer using one of the well-known methods in this area called Voussoir beam. This topic is not as general as a previous presentation, but I promise to keep it very simple, and I promise Dr. Dusseault no complicated mathematical equations. Let's go to the outline. First of all, I'm going to talk about the geological aspects of the problem, the roof layer of an underground opening, and then I get to go to the Voussoir beam method, different modes of failure, and I'm going to briefly explain the basics of the basic ideas of this method. And then a stress analysis of the beam, which is more kind of a verification of this model, and then factors of safety against failure modes. The thing is that we try to solve the stability assessment problem to come up with some safety zones for the roof layer. So we define some factors of safety and some diagrams to try to keep the roof layer stable. And then the conclusions of this method, as much as we can talk about it in this presentation. All right, this is a very, very simple figure for an underground opening here. This is a hollow space, if I can know how does it work. All right, here. We have a hollow space here. Let's say it's an underground opening, and this is the media around the opening. You see these parallel laminations, horizontal laminations, and then these joints close to vertical cross-cut these layers. The rock mass behavior is fairly governed by these laminations and different joint sets in such that these joints reduce or in extreme case eliminate the tensile strength of the material. If you want to show some more accurate and more realistic figures for the underground opening, you see again these parallel laminations here, both in horizontal slope and then inclined opening over here, and then different joints, vertical and close to vertical joints that you might see. The thing is that on top of a underground opening, like a cavern, these layers tend to separate from each other. You see this space from these two, also over here and here. The thing is that these layers tend to transfer the gravitational load laterally to the abutments rather than vertically to the beam underneath. This would cause to the idea that the stability of an excavation depends on the stability of the immediate roof. So for stability purposes, I just need to analyze the immediate roof over here that you might see. This is the opening over here, and this is called the immediate roof layer on top of the cavern. Because of these joints, I can assume that these layers are composed of different blocks of rocks. And since these gravitational loads are transmitted laterally to the sides of the cavern, to the abutments of these layers, it looks like an arch shape within the beam. This shape over here, this is the distribution of the compressive stress within the beam. So I'm assuming that I have a roof layer composed of two blocks here and this one joint at the middle, all right? And this shape, this curvature is the compressive zone, compression, all right? And top edge over here, and also at the bottom of the midspan here, I have the tensile zones, all right? This arch shape, this distribution of the compressive stress is called arching effect. That causes the transmission, lateral transmission of the stress to the abutments. All right. Assuming these blocks for the layer, this one and this one, I can say that the roof layers are composed of different blocks of rocks. Each of these blocks are called Voussoirs. This Voussoir term is adopted from the ancient Rome architecture. You see in different buildings or bridges these arch shapes. These are called Voussoir structures. Because of the arch shape distribution of the compressive stress within the beam, this method is called Voussoir beam. This is where the term of Voussoir came from. All right. Assuming the concept, the basics of the roof layer, we can assume three different probable failure modes for roof layer. The first one is the snap through, or somehow we can call it buckling over here, number A, over here. When the deflection of the midspan exceeds from a limited point, we see this snap through failure over here. The second one is crushing at the abutments, these 2 points here, bottom edge of the beam, and then at the top midspan due to a high concentration of the compressive stresses. And then the third one is shear failure or sliding at the abutments. It happens for high thickness of the beams that you see in this figure. It cannot tolerate tensile stresses, and then you see the shear sliding at the abutments. These three are most likely failure modes that could happen in underground openings. All right, about the basic idea of the Voussoir beam. The main equation is the equilibrium of the moments over here. This is a very, very simple equation, just a balance for moments. The thing is that the moment generated by self-weight of the beam must be compensated by the moment generated by the deflection at the midspan. If in these circumstances, then the beam would be stable. If it's not compensated over here, we don't have this equation, then it's not unstable, all right? Knowing the span thickness, the values of the unit weights, and different properties of the material, we can come up with an iterative equation to get the midspan deflection and then the lateral stress at the abutments. These two are the unknowns that we're looking for to define some factors of safety at the end. Remember that I said the stress distribution within the beam looks like an arch, and that's because the method is called Voussoir beam. Just to clarify this idea and verify this, I've used a software called UDEC. It's based on distinct element method, and it's to model the discontinuum media. I've used UDEC to simulate the stress distribution within the beam. So assume that I have a roof beam, and this is actually a half of it because of the symmetry. And this is the thickness of the beam. It's assumed to be 1 meter. And then this is the length, which is equal to the half of the span. And I have different cross sections through the beam. And I wanted to see how the stress varies at each cross section. I want to know that the distribution of the stress within the beam, how does it look like? So I have this, the maximum compressive stress at the bottom edge over here. All right, it goes to 0 on this part, and at the top edge over here, it's tensile. So I don't have any compressive stress over here. And as I go to the midspan, this part is the middle of the Voussoir beam over here. As I go to this end, gradually the distribution goes up, and then at the middle of the span, which is here, all right, you see that the concentration of the compressive stress goes to the top. So, and I left this part open because it doesn't matter what length of the span you use. It doesn't matter. I just assume it's 10, and I assume 9 cross sections. But whatever it is, I just wanted to show the distribution of this stress. How does it go from the bottom edge to the top midspan, which is the high concentration over here. It goes up, and at some point you see over here it looks like a rectangular, and the compressive stress is fairly equal at the bottom and top of the beam, and it goes to the here, which is concentrated at the top, and then the tensile stress at the bottom. That's why I said that the compression failure happens at this part and top midspan over here. Here, yeah. I can, having these distributions, I can track the centroids of this each distribution over here. For example, I would say the distribution of this, if I assume that this is a rectangle, I can have the centroid, for example, over here, and it goes to here, it goes up usually to over here. All right, if I track, I can make a reaction line of this stress. All right, so it goes to here. From this part, again, this is the thickness, this is the half span, and then this is the locus of the centroids of each distribution. This is exactly what I expected to see. This is a curvature that, well, imagine that we have one more at the other side. This is the half span, so it looks like an arch. All right, that I see this assumption in a simulation in reality. Let's go to some of the results. It's not all we can get from the Voussoir beam, but just for better understanding, let's discuss about some of the results, some sensitivity analysis. This figure shows the axial compressive stress with respect to beam thickness for different spans, 3 meter, 7 meter, and 9 meter. As the beam thickness increases, you see that the axial compressive stresses decreases. But when the span goes up from 3, 7 to 9, axial compressive stress, which is the maximum horizontal stresses, goes up. All right. So that means that in case of high span, high length, low thickness, I might see a failure due to crushing and a snap through, which we'll get to that. The other one, just for clarification, these solid lines are the data from the other researchers that I could find in literature, and these data points are the data, the results of my solution using MATLAB. The other one is factor of safety. Remember I said that the whole purpose is to generate some factors of safety, to have some diagrams, to know some limitations for the thickness and the span. I have, for example, in this plot, I have the factor of safety against shearing with respect to beam thickness. As the thickness goes up, all right, the factor of safety goes down, all right? So the safety decreases. And also I can have this one for different friction angles over here for 20 degrees, 40, and 70. As the friction angle goes down, again, the safety goes down, all right? This is for sliding for sure. Friction angle depends, the shear sliding depends on the friction angle. This is another factor of safety. This is against compression or crushing at the abutments and midspan. As the beam thickness goes up over here, and then you see that the factor of safety increases. So this is physically makes sense. This physically makes sense that we have more safety in terms of for this mode of failure in terms of big thicknesses. And then different spans, 5 meters, 8 meters, and 14 meters over here. As the span increases from the top, this line, to the bottom one, you see that the safety decreases. This is exactly what we were expected to see. Again, these solid lines are the data generated from the other researchers using numerical simulations and analytical solutions, and these data points are what I got from the iterative solution. It was just a general view of the Voussoir beam method. Just wanted to say that using Voussoir beam method, and definitely along with some numerical verifications and some considerations, it could get some better understanding of the safety of the unstable zones, stable zones that we're looking for different span to thickness ratios. As we saw in the figures, for example, some of the data we can get from this method, in case of low span to thickness ratios, the failure of the slip or shear sliding would happen. It's most likely to happen. In terms of high span to thickness ratios, crushing at the abutments and mid-span, and also snap-through failure would be expected to see. Having said that, generating different diagrams of the factors of safety, again, modes of failures, could get a good understanding of the limitations that we might have for the generating of the cavern, different span, different thicknesses that we are allowed to have for long-term reserves of the salt air, compressed air. I want to thank to my supervisor, Dr. Dusseault, Dr. Basu, who's not here now, my colleagues in CS Research Group, and also the Waterloo Institute for Sustainable Energy. These are the references that I used. Thank you so much. I'll be happy to answer your questions.
Thank you. I do have a question from the web. It's for you and for Jay. Where's Jay? You could come down here just in case. I do have a question from the web. So a gentleman has sent a question, and he says in general he likes that this work is towards determining a factor of safety in the roof stability and comparing it to the literature as much as possible, because the mining literature might indeed be
for sure.
good. I mean, the mining literature is almost the only source of information in this business. And the question that he had for both of you, or either of you, is that in horizontal caverns, for which we don't have a real field experience yet, how does the shape of the cavern affect the choice of minimum and maximum pressure limits that you might have?
Do you want me to answer?
Either of you, or one after the other?
I can go first and then add some comments for sure. Well, in laminated layers in a horizontal cavern, what we see, as Dr. Dusseault said, that we don't expect to have a fancy cavern with very nice and clean with a roof of elastic or salt. All right, we might have an elastic roof at some point and also salt roof at some other points. So definitely it matters that what kind of roof we are looking for. in case of salt as the roof, again, for the modeling of the roof stability, we should use those creep models that we generate for the shrinkage of the cavern, for the other parts, not the roof stability. In case of an elastic roof, Voussoir beam is one of the models that we can use. For having both in the same cavern, we have to do some parametric analysis to see what span we have as an elastic, if it's going to be shale or anything else, and what span we have for a salt behavior, for a salt material, and try to model that creep behavior. Definitely, it's not completely investigated in the literature. We don't have at all any horizontal caverns so far. So this is what I came up with for the answer.
I think for the long horizontal caverns, what we need to understand is that the diameter will be around 25 meters to 30 meters. I don't predict that there will be much roof issues. So the minimum maximum should not be different, but this is just my opinion. And I think as I said in my slide, the maximum pressure should be less than 80% of the cap rock fracture pressure, and the minimum pressure should be at least 25% of the lithostatic pressure. But if you're looking for some answer, like in terms of how the maximum minimum pressure will be different in long horizontal galleries versus long cylindrical caverns, I don't think that will be much of a problem in long horizontal galleries because roof will be well supported. Yeah.
Yeah, I think the key point is that in a long gallery, like a very, very long Oktoberfest sausage, you can make the roof span fairly small and still achieve the volumes that you want. Because we do have salt caverns, the cylindrical ones, in the world where the roof span is much, much larger than 50 meters, or even approaching 100 meters, where the roof is still stable. But the key factor is that those caverns are generally not pressure cycled. They're caverns for the storage of materials at a constant pressure, or maybe they're cycled in pressure once a year, like a natural gas storage cavern. Typically, it's cycled once a year in pressure. We don't really have a deep understanding yet of how the Voussoir beam analysis or the other models will inform us and help us understand how cyclic pressurization in a cavern will affect the roof stability. That's part of the research. And we won't answer all the questions. We'll have a stab at it. So a couple of questions over here. Dr. Jackson?
Mahdi, you were using the Voussoir data.
Yeah.
I'm wondering if the data from the waste isolation pilot plant, which is embedded salt in New Mexico, Carlsbad, New Mexico, which is an operating nuclear waste facility. And I went down there 10 years ago before it started accepting waste, and there was spalling from the roof, I noticed. And I think that would be your snap-through model. But I'm sure there must be some geomechanical information on the cavern roof. That there were very long horizontal tunnels there as well. So I think it's very apropos to your study. And I'm sure Los Alamos or Sandia have published results on the website. But tell me more about the Voussoir data. What is that? What does that concern?
The last one over here?
Yeah.
Yeah. The researchers in this area are not too many. Professor Kaiser, that you may know him, in Canada, Dr. Sofianos and Dr. Voussoir are the main researchers in this area, also with Brady and Brown from Australia. Dr. Voussoir analyzed this method with Voussoir beam and kind of came up with a better idea, well, in his opinion for sure, a good idea, different idea, which is called DDA over here. So he generated this method, DDA, over here, and verified his model against Voussoir beam. So what I used from Dr. Voussoir data is the Voussoir part, all right? Those data that generated from this point of view, and then he used this data to verify with DDA.
Yes, but what was the roof collapse in? What kind of material, rock, was it in?
Well, I don't exactly remember now what kind of material was in the roof in this case that collapsed. I have to go through to this paper again, and I will come up with the answer for sure.
I think that Dr. Jackson has actually made a very good point. We also have many, many salt mines in the world that have long travel ways, and the behavior of those might be helpful. However, they are not subject to cyclic loading, and they are designed for very different purposes. nevertheless, that might be a good data source for us to establish at least some semi-quantitative limits. Dr. Fraser?
In my so can you go to a picture of your arch? Any one of them. Yeah. That one's a great one.
Okay.
Okay. So my experience with mechanical systems is that these types of compression and sort of tension and systems work well when you have a homogeneous system, the predictions. What concerns me, well, maybe it doesn't concern me, what I'm interested in is the fact that you're going to have the salt beds in the elastic region, and when you have two different materials, distinctly different, there can be slippage and things can change.
Yes.
And so a segment that was under compression goes into under tension and then goes back to compression. You
Yes,
may or may
I
not,
saw.
might be the annealing effect or something else. I'm wondering how your model, so I'm not asking you to
Yeah,
predict
I know.
what's going to happen,
For sure.
but I'm wondering how you would predict modeling that interface between the two and any associated problems you can anticipate.
All right. Okay. Yes, it's a good question, really. The thing is that we can answer. I can answer this question in different aspects. One thing is that I said over here that we have these layers up and down at the top of the cavern. All right, and these are fairly separated from each other. And it's also experimentally observed that this would happen for a cavern roof. So it's a quite assumption. It's a simplification for the sake of simplification that we have just one layer at the top. It's called immediate roof, and we can analyze this method. All right. But the thing is that also we can use this Voussoir method to analyze different layers, sub-layers. So somehow we can deal with that non-homogeneous media.
Go back to
This one?
Sure, a little bit more clarification. In a cavern, in a very simple model, you might look upon this as the elastic rock, and the salt rock is here in the abutments, okay? And this material, and it depends upon your pressure limits and your depth and your temperature, this material is behaving viscoelastically or elastoplastically. I mean, elastoviscously. It's moving, it's creeping. So that this interface turns out to be an important interface of slip. That requires a composite material model. Right now, Mahdi is using a discrete element model, and I believe that the discrete element model cannot use a creep law yet at this stage. So what he has is a model like this. He can introduce a plane here in the abutments that will be weak enough to allow slip. He can do that. But he can't yet make this material into a viscous material. Okay, so that's probably going to require some double modeling, where you've got a discrete element model combined with some kind of a finite element model that will allow creep. Because the discrete element models, none of them have any creep capacity yet. That's fairly hairy for a discrete element model because of the geometry issues.